These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medium for medical education. If this is the first time you are viewing a program in this optics series, send an email to jyoungmd@gmail.com with your name, position, institution, and city, state, or province, and country. Thanks, and enjoy the podcasts. Today's discussion deals with magnification and with central ray tracing. Way back when we discussed vergence, we said that there are 4 questions that you can potentially be asked on a lens image object problems. And they are, what is the power of the lens or the location of the images and objects? And I said that was all sort of one question. And we solved that with vergence. And question 2 is, is the object real or virtual? Is the image real or virtual? And I said we would solve that with vergence too. The other 2 questions, is the image inverted or upright? And what is the size of the image relative to the size of the object? Are questions that have to be solved using central ray tracing. So we're going to deal with that now. So let's look at this problem here. Let's define, first of all, what we're going to be talking about. Transverse magnification is the height of the image. And by height, what I mean is the direction of the image that is perpendicular to the ray of light that is passing from that image through the lens. Okay, so our rays of light are moving from the left side to the right side, are moving horizontally on this sheet of paper or slide. The direction that we're going to measure the object and the image in, therefore, is in the vertical. And we refer to that as transverse mag, being the height of the image over the height of the object. Okay, so we've drawn out here a fairly standard vergence diagram where the rays of light start out at the object. They hit the lens with a vergence of -10. Right, the vergence right before they strike the lens right over here is going to be -10. Why is the vergence -10? When I ask you what the vergence is, you answer with a question. The question is, where do the rays of light converge relative to where we are? And they converge 1/10 of a meter, therefore the vergence must be 10, and to the left means minus. So -10 plus 5 means the vergence coming out has to be -10 plus 15 means that the vergence coming out has to be plus 5. Plus 5, always and forever, means that the rays of light converge 1/5 of a meter to the right, and that's what's shown here. This is a vergence diagram. The rays of light start out at a point, and they end up at a point. These rays of light describe what is going on at the base of this candle. Rays of light coming off of the base of the candle. Now, I want you to notice that there is one special ray here. There's one ray that passes through the center of the lens that emerges from the lens undeviated. You also know that there are bundles of rays coming off from other parts of the candle, from the middle of the candle, from the top of the candle, and that they are also passing through the lens and are forming points along the image here too. Amongst each of those bundles, there is also one special ray, one ray that passes through the center of the lens and emerges from the lens undeviated. And we refer to those all as central rays because they are the rays that are in the center of the bundle passing through the lens and are passing through the center of the lens. When we want to figure out what the height of an image is, or the height of an object, we can figure that out by knowing the distance from the object to the lens, or from the image to the lens. And I'm going to show you why in the next slide, and I'm also going to show you an example of a central ray diagram, which is distinct from the vergence diagram in that the rays of light do not start and end at a point. So this is a central ray diagram, and what we're looking at along the base of the candle is we've only taken the one ray that passes through the center of the lens and emerges from the lens undeviated. We've done the same thing for the top of the candle. We know that there are a whole bundle of rays coming out from here, but there's one ray that goes from the top of the candle through the lens and emerges from the lens undeviated. This central ray diagram will not show us where the image is formed. We need to use our Virgin's calculations to determine where the image is or where the object is before drawing central rays. However, what the central ray diagram tells us is wherever it is that the image is formed, the ray that started out at the base of the candle is going to intersect with the base of the candle in the candle's image. And the ray that started out at the top of the candle is going to tell us where the top of the candle is. Okay? So we don't know from the central ray diagram where the image is formed, but we know that wherever it is formed, that the top of the candle must lie along this line, and the bottom of the candle must lie along this line. So this is how we use central ray diagrams to determine what is inverted and what is upright. We can also make this diagram into two congruent triangles. And we do it like this. Now we have similar triangles, and they're similar because this angle here is the same as this angle here. Therefore, the ratios, think back to high school here, the ratios of the bases is the same as the ratios of the heights. So if we know that this base is 10 centimeters and this height is 3 centimeters, and we know that this base is 20 centimeters, then we know that this height must be 6 centimeters, right? 20 over 10 is equal to x over 3. So x must be 6. In this problem, both the object and the image are on the same side of the lens. In this case, the object is the larger candle here, and the image is the smaller one. You could have solved that using Virgin's, I am sure. And indeed, this is a Virgin's diagram because it starts at a point. The rays of light start at a point and end at a point. And what we're going to do now is we're going to make it into a central ray diagram. This is the central ray here. We've drawn it from the top of the object through the center of the lens, where it emerges from the lens, of course, undeviated. And we know that the base of the image lies along, that the base of the candle in the image lies along this line, and that the flame of the candle lies along this line. Of course, with central ray, we cannot determine where the image is, but we know beforehand, using our Virgin's calculations, that the image is where it is, that it's right here. And then we're going to turn these into triangles, and we can say that the magnification in this case is equal to 0.5. So when the image is smaller than the object, it's a fractional mag. It's not a negative mag, it's a fractional mag. This is a very similar problem, except in this case, the object is this guy over here, and the image is this one. And we have not a -5 lens, but a +5 lens in this case. We're going to draw a central ray, and as always, we draw the central ray from the top of the object through the center of the lens. This time we need to extrapolate it backwards so that it hits the image. And so we're going to do that right here. We've extrapolated it backwards because you need to get it to the point of where the image is. And of course, we've calculated the image beforehand using Virgin's. And this time when we do our calculations, we find that the mag is equal to 2 times. transverse mag. Now, one question that you may be asked is, what is the image of something on the retina? And, a person's looking at an object that is 6 feet tall, that is 10 meters from him. What is the image on his retina? Well, you know the base of triangle 1, which is 10 meters, and the height of the object, which is 6 feet. And by the way, the height and the base of the triangle don't have to be given in the same units. You can still solve it. What you don't know is what the base of the triangle is inside of the eye, and I'm telling you now it's 17 millimeters. Is it always 17 millimeters in real life? Of course not. But for the purpose of calculating for optics problems, you're going to use the value of 17 millimeters. Okay, here's something really easy. Axial mag, which is what the magnification of the object is along the direction of the rays of light, not perpendicular to them. So this is our same problem with the 3 centimeter tall object that I'm giving you now is 1 centimeter wide. It is twice as tall in terms of transverse mag. In terms of axial mag is equal to transverse mag squared. So if it's twice as high, it's 4 times as thick. A problem might go something like this. You're examining a patient's optic nerve, and in your optical system, the optic nerve appears to be 3 times as high. Well, as high means it's giving you transverse mag. The question is, how much deeper does the optic cup look? If it's 3 times as high, the optic cup must look 9 times as deep. And because axial mag is equal to transverse mag squared.